Hello students, welcome to a new lecture of P block elements. In continuation with the last video, we are starting with the next element of oxygen, which is ozone. In the last class, we have seen the compounds of oxygen like dioxygen and ozone is what we are going to see now. Or oxides also we have seen, dioxygen also we have seen. Now the next compound is ozone. Ozone, what is the formula? Is O3, right? The formula of ozone is O3. So this O3 is having its very strong power of dissociation. You cannot store ozone gas for a longer duration of time. If you want to store, it is only possible for a short period of time. If you store it for a longer period of time, that ozone dissociates into oxygen gas and nascent oxygen. Right? Therefore, storage is not for a longer period of time. Now, coming to its preparation, how can you prepare ozone? Is if you take oxygen gas and supply a strong electrical discharge. If you take oxygen gas and give electrical discharge, in the presence of electrical discharge, if you slowly pass oxygen gas, it will be converted into ozone. How many ozones I got? There are 4, right? Nascent oxygen. Or simply I can take 3O2 and 2 ozone. This is the reaction in which ozone can be prepared, but the condition should be you have to give oxygen gas very slowly in the presence of electrical discharge, right? There are not many preparation of ozone, but ozone have so many properties with different compounds, right? Why is it having so many properties with different compounds? Because this ozone is unstable. I told you cannot store ozone for a longer period of time, and it is unstable. If it is unstable, it is even very reactive. If it is reactive, what will it give? It is unstable, reactive, and converts ozone into oxygen gas and nascent oxygen. It has the ability to release oxygen in the form of nascent oxygen, right? So because of this capacity of releasing the nascent oxygen, ozone acts as a very strong oxidizing agent. What does it mean by oxidizing agent? Is by releasing oxygen, nascent oxygen, it can help others to undergo oxidation. So if you react ozone with any of these compound, ozone will oxidize them. Right? Ozone will oxidize them. Oxidation of lead sulfide will take place. Oxidation of iodide take place. Oxidation of the metal silver takes place. Oxidation of potassium iodide used in titration. You can use even ozone even there. Oxidation of ethylene into its ozonide. Oxidation of nitric oxide into its corresponding oxide also is possible. Why? Because ozone has as ozone is very much reactive, it cannot be in the form of O3 for longer. So if you take ozone, it will immediately dissociate into oxygen gas and nascent oxygen. This is called as oxygen gas. When I say oxygen gas, it should be in the form of O2 only. Oxygen gas cannot be in the form of O. But if I say just O, it is nascent oxygen. So ozone has the ability to oxidize others. Why? Because it is releasing nascent oxygen. So now what we will see, different properties of ozone with different compounds, right? How many? There are so many varieties of compounds with which ozone can react. What is the first compound I have taken? Is lead sulfide. What is the name? Lead sulfide. The color of this is black. So you can call it as black lead sulfide reacts with ozone to give you lead sulfate, which is PbSO4. What is happening here? Oxygen is getting added. What does that mean? Addition of oxygen is nothing but oxidation. So in this list, all of them takes oxygen from ozone. So all of them are undergoing oxidation, which is nothing but addition of oxygen. First compound I have taken is lead sulfide, which is undergoing oxidation to get converted into lead sulfate. Same way, iodide also reacts with ozone to give you iodine gas. There are many definitions of oxidation, which is, one definition is, two definitions in fact. One definition is oxygen is directly added, that is also called as oxidation. The other definition is losing electron is also oxidation. As we have seen in electrochemistry, loss of electron is oxidation and gain of oxygen atom is also oxidation. So in the first reaction you are adding oxygen, therefore it is oxidation. In the second reaction you are removing electrons from iodine to get converted into iodine. From iodide you are removing electrons to get iodine gas. Is it loss of electron only? Yes. Therefore is it oxidation? Yes. Who is doing that oxidation? Is ozone only, right? What is the next? It reacts with silver. It reacts with silver also to give you silver oxide. Silver oxide having +1 oxidation state on one silver, +1 oxidation state on another silver. Oxygen has -2, so it should be +2. Therefore on each silver the charge is +1. So this is neutral, that is +1. Are you removing electrons? Yes, right? Therefore it is oxidation. Are you adding oxygen? Yes. So it is oxidation covering two definitions, right? Who is doing that? Ozone only. Now these are the reactions of ozone in which it is oxidizing different substances. Because of this property of oxidizing iodide into iodine, because of this property of oxidizing iodide into iodine, ozone is used in titration, where iodide solution is titrated with ozone to give you iodine, which can be captured with a standard reagent called as hypo, right? So in titrations we use hypo as a standard solution, but to get iodine gas you need ozone. In the beaker what do we take? Potassium iodide solution. To that ozone is passed. If you pass ozone to potassium iodide, what happens? You get iodine gas. If that iodine gas is treated with Na2H2O3, if Na2H2O3 is taken in the burette and iodine is released in the beaker, if you titrate you will get the readings from which you can calculate concentration of beaker solution or even hypo solution also. So, right? So, during titrations it is because of ozone only which is acting like oxidizing agent to get you the end point, right? Because of ozone only you got iodine, and because of iodine only you got end point, and because of end point only you are able to calculate the readings, right? So, this is also a place where ozone is used. Now, it does not mean that ozone reacts with all the inorganic compounds only, because ozone has its ability to give oxygen. It can react with organic compounds also. What is the example of organic compounds I can take? Ethylene or ethene. When ethene reacts with ozone, you get ozonide of that ethene. How? This way. This is called as ethylene ozonide. You calculate the valency of carbon 1 2, 3, fourth one is hydrogen. Same way 1, 2, 3, fourth one is hydrogen. So it is satisfied. Because of a double bond, ozone can come and add into the double bond to give you that particular ozonide. If you take ethylene, you get ethylene ozonide. If you take propylene, you get propylene ozonide. Which particular compound you take, that ozonide you will get. So are you adding oxygen inside the molecule or not? Yes. Is that oxidation of alkenes? Yes. So ozone is used for oxidation of alkenes into its ozonide. That alkenes can be broken down to give you different compounds. Different compounds you can get. You can get different compounds and they are aldehydes. Okay. So till here only you write which is alkene react with ozone to give you ethylene ozonide, right. The next property of ozone, as where is ozone present? Ozone is present in the stratospheric layer which covers the earth surface and protects the earth surface from our atmosphere from harmful UV radiations entering inside the atmosphere, right. So ozone is a very protective layer outside our atmosphere which was very thick. But as the days pass, the thickness of the ozone is getting reduced, which is called as was depletion of ozone. Do you want ozone to get depleted? No, you have to protect the ozone layer from getting depleted. If it is not protected, that means so many holes will be formed in the ozone and harmful UV radiations will be entering in the atmosphere, which is very harmful for both plant life and animal life, right. Now that is ozone depletion. One of the major factor of depletion of ozone we know till now was freons. Where from these freons comes? It comes in refrigerants. Whatever refrigerant you use in AC and refrigerator are having chlorofluorocarbons which are released into the atmosphere, and if they release into the atmosphere they will go directly to ozone, react with ozone and deplete ozone, right. But apart from freons, something else is also responsible for depletion of ozone that we have never thought before. But in our experiments in the laboratories, they have observed that whenever nitric oxide is added to ozone, ozone will react with nitric oxide, they have observed. They used to think that ozone cannot react with nitric oxide, but by doing many experiments they found out that ozone will react with nitric oxide also. If it reacts with nitric oxide, what do you get? Nitrogen dioxide plus O2. This reaction indicates what? Ozone is able to react with nitric oxide. What happens? Is ozone getting lost or not? That means, can you call it as depletion of ozone or not? Yes. Because of this reaction, we came to a conclusion that not just freons, even nitric oxide which we are releasing here is also responsible for depletion of ozone. Whatever nitric oxide is released in the atmosphere because of pollution of automobiles will go into the atmosphere or stratosphere and causes ozone to deplete. What is the proof? This reaction is the proof. If ozone cannot react with nitric oxide in the laboratory, that means ozone layer in the stratosphere also don't react. But in the laboratory we have seen that ozone is very good at reacting with nitric oxide. That means even there also reaction must have taken place. That's why ozone got depleted this much, right. So all these reaction, in every reaction you will find that ozone is acting like a very good oxidizing agent. Because of this property, ozone has many uses also. What are those? Ozone, by releasing nascent oxygen, can be used for purification of water, right? In the advertisement we see ozonized water. What does that mean? If you treat water with ozone, it releases nascent oxygen which will kill the germs. So, it acts as disinfectant, and even by killing all the harmful germs, it will protect the water from harmful bacteria, right? So, these are the uses of ozone, its preparation and its properties. Whatever reaction we have seen for preparation, the opposite reaction only takes place for the properties of ozone, as ozone is not stable, right? Therefore, these reactions involve releasing of nascent oxygen, thereby acting as an oxidizing agent, right? So, we have finished the compounds of oxygen. What are the compounds of oxygen? O2, all oxides. We have classified oxides also into acidic oxide, basic oxide, amphoteric oxide and neutral oxide, and then comes ozone. These are the three compounds of oxygen. Now, what is the next element of 16th group? Sulfur. So, what we will see? We will see all the compounds of sulfur, its allotropes also we will see. Okay. Now, just like phosphorus, we have seen two allotropes of phosphorus. Three allotropes of phosphorus we have seen. That was white phosphorus, red phosphorus and black phosphorus, right? Same way, even sulfur also has its allotropes, right? Allotropes of sulfur are two. You have two allotropes in sulfur, and it is alpha form of sulfur, it is called as alpha form of sulfur, and beta form of sulfur. What is the shape of alpha form of sulfur? Is rhombic or yellow sulfur we call rhombic sulfur, and this one is called as monoclinic sulfur. Right? One allotrope is called as rhombic sulfur, the other allotrope is called as monoclinic sulfur. Let us look at the special features or properties of rhombic sulfur and properties of monoclinic sulfur. Rhombic sulfur, it melts at lower temperatures, say around 360, 370 like that Kelvin. Right? That means it is stable, melting point is around this much. What does that mean? It is stable at room temperature. Stable at room temperature. What is the room temperature? 273 Kelvin is the room temperature, right? So, this sulfur, this form of sulfur is stable at room temperature. If you want to if you want to convert rhombic sulfur into monoclinic sulfur, you have to heat it above this temperature. If you heat this above this temperature, that means you will get the next allotrope. What is the next allotrope? Monoclinic sulfur. What is the melting point of monoclinic sulfur? It is higher than this. It is around 390 Kelvin is the melting point of monoclinic sulfur. Right? Monoclinic sulfur is stable at a higher temperature, which is around this. That means if you want to convert rhombic sulfur into monoclinic sulfur, you have to heat it till 369 Kelvin. Till 369 Kelvin, if you heat, the rhombic sulfur will remain as rhombic sulfur till this temperature, but after 369 Kelvin, rhombic sulfur will be converted into monoclinic sulfur. That means at this temperature, it is called as transition temperature. Both alpha form of sulfur as well as beta form of sulfur you can find at this temperature. But if you increase the temperature more than 369, you will get only beta form. If you decrease the temperature less than 369, you will get only alpha form. At this temperature, both of them are stable. But before this temperature, only alpha form of sulfur is stable. After this temperature, only beta form of sulfur is stable. Therefore, this temperature in which both the allotropes are stable are called as transition temperature. What is the transition temperature of sulfur? If the question comes, you should write the transition temperature is the temperature at which both monoclinic as well as rhombic sulfur are stable, which is 369 Kelvin. Before 369 Kelvin, only rhombic sulfur is stable. After 369 Kelvin, only monoclinic sulfur is stable, right? That is about these two forms. And if you take chemically different allotropes of sulfur, you have so many allotropes ranging from S6 to S20, but the most stable one which is isolated is S8 and S6. S8 and S6. What is the shape of S8? Is like a crown. Is like a crown. The shape of S8 sulfur is like a crown. This is where sulfur is present. This is where sulfur is present. This is S8. What is the shape of S6? It is just like the chair conformation. Sulfur, 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 sulfur and sulfur. Both the rings are puckered rings in order to avoid any strain in the molecule. One is S8 allotrope, another is S6, right? These two are isolated. Okay, there is one more allotrope of sulfur, chemically I mean, which is S2. But this S2 allotrope is obtained at a very high temperature of around 1000 Kelvin. If you increase the temperature around 1000 Kelvin, then you will get a type of sulfur which is S2. You have a molecule called as O2, right? But it is available at normal temperature also. What is the nature of oxygen gas? It is paramagnetic in nature, right? It has lone pair of electrons, therefore it is paramagnetic in nature but at normal temperature. Same way you get S2, but it is not in the form of a gas, it is in the form of liquid, right? That sulfur are in the form of solid or liquid, but it is not a gas, and that also behaves paramagnetic. But its paramagnetic nature, when can you see? Only at this temperature you can see the paramagnetic nature of sulfur. In the exam you may get a 2 marks question asking which sulfur exists as paramagnetic nature. That means you have to write S2 exists in the form of paramagnetic nature at a very high temperature of 1000 Kelvin because of its lone pair of electrons, just like O2, right? This is about allotropes of sulfur. S8 from S6 to S20 is the normal range. S6, S7, S8, S9, so many are possible. But the most stable which can be isolated and studied are between these two range. This is not a stable molecule, it is unstable. It can be stable only at this temperature, therefore it is special. What are the normal range? S6 and S8. What is the shape of S8? Crown shape. What is the shape of S6? Chair conformation, right? So these are about allotropes of sulfur. Now we will see different compounds of sulfur. One is oxoacids of sulfur, another is sulfur dioxide, another is sulfuric acid. But sulfuric acid is not there for us now, so we will study only these two, which is oxoacids of sulfur and sulfur dioxide, okay, in the next class. Thank you.